Okay, so some other basics. Modulus, the modulus and argument of a complex number. Modulus and argument. Okay, so modulus and argument. Basically, if we go back to the Argand diagram of a complex number, here's any point x plus iy. So now obviously if we draw this line from the origin to this, keeping in mind, of course, this is your real axis and this is the imaginary axis. So this is the Argand diagram of the point x plus iy. Now we call the modulus of z, okay, which is the size of z in fact, and it would be essentially x squared plus y squared under the root. Okay, so it's the real part squared plus the imaginary part squared. So it's the size or the size of this line essentially that you see here. Size of this line would be x squared plus y squared. It is very similar to modulus or the magnitude of a vector, for instance. Okay, similar to that. The idea is very similar to that. Argument of z, on the other hand, written as arg z, ergz, argument of z, is equal to theta, where the tan of theta, in fact, the slope of the line, is y over x. So it's the imaginary part divided by the real part. This is for, of course, z not equal to 0. Because if it's equal to 0, then we can't have basically infinite slope. So anyway, it's going to be a 0 over 0 situation. So we can't. So we have to avoid that. Okay. So these are some basic definitions. Knowing that now the modulus of z is square root of x squared plus y squared, we end up with another interesting relationship between the conjugate and the product of the conjugate with itself, of a complex number with its conjugate, is in fact, if you remember, it's x squared plus y squared, but that's very similar to the modulus of z, in fact, squared. So it's the modulus of z squared. That's an interesting thing to keep in mind. You will notice that this has a lot of similarity with vectors if you've already studied them. This looks very much like when we look at inner products, the relationship between the dot product and the norm. It looks very similar to that. Just in case you've already covered it, it's nice to look at something familiar. So now, given a complex number, for instance, and by the way, here we assume, of course, that argument of z, okay, is between minus pi and plus pi. Okay, argument z is between minus pi and pi. Okay, this is known as, in some places you might call, this is called the principal value. Okay. Now, let's take an example. Say, for instance, 3 plus 2i. So 3 plus 2i has modulus if its size is essentially going to be 3 plus 2i mod is square root of 3 squared is 9 plus 4. So it's square root 13. Okay. And its argument, the argument of 3 plus 2i is in fact, it's calculated as follows. We say tan theta is 2 over 3. So theta is the tan inverse of 2 over 3. Okay, so that turns out to be, in radians, that's be 0.588. 0.588, okay? So then that argument becomes 0.588, okay? So that's how we calculate the argument. Now keep in mind, again, when angles are involved, especially in a coordinate system, it is important to know. My advice to you is, a lot of students get confused about drawing the argument. Best thing is, look, quickly draw where the point is in which quadrant. That's what I mean. Angle. Should you add 180? Is it going around? Is it minus 360? Where is the angle? Quickly, what you should do is, this is 3 plus 2i. So 3 plus 2i means it's in the first quadrant. So that means the angle, the angle we're talking about is this angle here. This is theta. Okay, so that's it's at 0.588 radians. There's your angle. Now, if you had, for instance, the number, say 2 minus I. Okay, if I were to plot 2 minus I, that would mean 1, 2, and minus I would be here, so it's down here. So that's mine. Now if I were to calculate this, what would happen is tan theta would be minus imaginary part over this, so it's minus a half. So it's minus a half, okay? So minus a half, the inverse of that, if I calculate it, you should be able to calculate that it would be this angle here, okay? So here theta So here theta comes to negative 0.464 radians. So you can see that angle, it's going to be this angle here. Okay, so just a quick idea that whenever you're calculating the argument, it's a good idea to quickly draw the actual complex number, its argand diagram, and then you can get a quick idea of what to expect from the angle. All right, I'm going to stop there. Those are the basics. We continue next video with the polar form of a complex number.